In propositional logic, we often write expressions that look different, but actually mean the same thing. Understanding when two logical statements are equivalent is the key to simplifying logic, proving identities, and reasoning clearly in mathematics and computer science. Today, we'll build this idea slowly and carefully, starting from basic logical behavior and ending with formal equivalence proofs. Before we can talk about equivalence, we must understand how propositions behave. A tautology is a proposition that is true for every possible assignment of truth values. No matter whether P is true or false, this statement remains true. A contradiction behaves in the opposite way. This statement is false in every possible case. Finally, a contingency is a proposition that is true for some assignments and false for others. So, propositions can behave in three ways: always true, always false, or somewhere in between. This classification will soon help us define equivalence precisely. Now we are ready for the central idea of this lesson. Two compound propositions are logically equivalent if their biconditional is a tautology. When this happens, we say that P and Q carry exactly the same logical meaning. Consider these two expressions. Although they look different, their truth values match in every possible case. That makes them logically equivalent. To work with equivalence confidently, we need reliable transformation rules. These are called logical equivalence rules. One of the most important transformation tools is De Morgan's law. These laws explain how negation interacts with logical OR and AND. When negation moves inward, the connective changes and each variable is negated. De Morgan's law are just two members of a larger family of equivalence rules. These laws allow us to rewrite logical expressions without changing their meaning. Some laws describe how propositions behave when combined with truth or falsity. These are identity and domination laws. Others explain repetition, order, or grouping, idempotent, commutative, and associative laws. And some laws, like absorption, help eliminate unnecessary complexity. Once we know these laws, we can use them to prove equivalence formally. Let's see how these laws work together in a complete transformation. Consider this expression. To solve that, we have to first apply De Morgan's law. Apply De Morgan again. Now distribute. The first part is a contradiction, so it disappears. This is the final form. This is how equivalence proves progress, not by guessing, but by controlled logical rewriting. Next, we move on to propositional satisfiability. A compound proposition is satisfiable if at least one assignment of truth values makes it true. So far, we have compared propositions based on whether they always behave the same way. Now, instead of comparing two propositions, let's ask a different question. Is it possible for a proposition to be true at all? This question leads us to the idea of satisfiability. A compound proposition is satisfiable if there exists at least one assignment of truth values to its variables that makes the proposition true. In simple terms, if you can find even one situation where the statement becomes true, then it is satisfiable. Consider the proposition. This statement says P is true and Q is true. If we assign true to both P and Q, the entire expression becomes true. So this proposition is satisfiable because at least one assignment makes it true. This proposition is even more flexible. If P equals to true or Q equals to true or both are true, the statement becomes true. So again, this proposition is satisfiable. Now consider this expression. This statement requires P to be true and false at the same time, no matter what values you assign to P. If P equals to true, then negate P is false. So the expression is never true. This proposition is unsatisfiable. Furthermore, a proposition is unsatisfiable if and only if its negation is a tautology. Take this. Its negation is negate P intersect not P. By De Morgan's law, we get this. This is a tautology, and that confirms our conclusion: the original proposition is unsatisfiable. So let's connect everything we have done. Tautologies and contradictions describe behavior. Logical equivalence compares meaning. Equivalence laws allow transformation, and satisfiability tells us whether truth is possible. When these ideas work together, logical expressions become structured, predictable, and much easier to reason about.